This is part 4 of a series on CNN. In this video, we will look at the residual neural network. This video was produced in Korean and translated into English. My voice is generated by AI, text-to-speech. Before moving on to 3D convolutions, let's look at the residual neural network, which can be used to build deeper CNNs. Let's look at the overall architecture for a residual network. And let's look at the structure of a small-scale residual network for the CFAR10 dataset. Finally, let's implement a small ResNet model to classify CFAR10 images. In 2015, Kaiming He et al. Proposed the residual network in this paper. This was briefly covered in the highway network video, but will be covered in more detail in this video. To achieve better performance, we need to build deeper neural networks. However, deeper neural networks are more difficult to train. This paper presents a residual learning framework to ease the training of networks that are substantially deeper than those used previously. In general, deeper networks suffer from degradation problems. This example shows that the errors in a deeper network is larger than those in a shallower network. Both the training error and the test error are larger in deeper networks. This is not caused by overfitting. If the training error is smaller but the test error is larger, this may be due to overfitting. However, this case cannot be considered overfitting because the training error of the deeper model is also larger than that of the shallower model. This phenomenon is called degradation in deep neural networks. The authors of this paper addressed this problem by introducing a deep residual learning framework. They proposed the following residual building blocks, which are the core components of residual neural networks. This shortcut or skip connection is added to a series of layers. Typically, these are convolutional layers. This connection allows the input to the residual block to be added to the output of these layers before the final activation function is applied. If the input and output dimensions of these layers are the same, you can simply add them together. Otherwise, you need to adjust the dimensions of the input x before adding it. This connection then allows gradients to flow more smoothly within the network during backpropagation, alleviating the vanishing gradient problem and enabling deeper networks to learn. For much deeper networks, the authors of the paper used a bottleneck building block like this. An example of a residual network with 34 parameter layers is shown in this figure. Initially, a 2D convolutional layer with 7x7 kernels and a stride of 2 extracts the features of the image. This is followed by a pooling layer, and we have multiple 2D convolutional layers with 3x3 kernels. These are shortcut connections. The layers marked with the same color have the same input and output dimensions. So the shortcut connection shown as a solid line can add input to output as is. As the color of the layer changes, the dimensions of the input and output also change. So the shortcut connection shown as a dotted line downsamples the input and then adds it to the output. We'll look at this in more detail later in the implementation code. This output is then passed through an average pooling layer and finally to a feed-forward network. This is the architecture of ResNet34. The input image has dimensions of 224 by 224 by 3. The initial convolutional layer has 64 7 by 7 kernels. And the stride is 2 and the zero padding is 3. So the output dimension of this convolutional layer will be 112 by 112. And the output dimension of the pooling layer will be 56 by 56. Building blocks are shown in bracket with the numbers of blocks stacked. The Con3x layer has a total of 4 building blocks. The output size continues to be halved. The number of filters continues to double. Downsampling is performed by Con3.1, Con4.1, and Conv5.1 with a stride of 2. Next, let's look at the residual network for CFAR10. Since the image size of CFAR10 is small, 32 by 32, we use a small residual network. The first layer is 3 by 3 convolutions. Then we use a stack of 6n layers with 3 by 3 convolutions on the feature maps of sizes 32, 16, 8 respectively, with 2n layers for each feature map size. The subsampling is performed by convolutions with a stride of 2. Then network ends with a global average pooling, a 10-way fully connected layer, and softmax. There are totally 6n plus 2 stacked weighted layers. If n is 3, a total of 20 weight layers are stacked. This is the ResNet20 for CFAR10 image classification. Let's take a closer look at this through the figure on the next page. The authors of the paper trained this network using these settings. During 64K training iterations, the errors decreased as follows. We can see that the errors are dramatically reduced at around 30K iterations. We will only iterate 1K times because this takes too long. Next, let's design this model in detail for the case where n is 3. The input image has dimensions 32 by 32 by 3. This model has 3 sets of layers. This is the first convolutional layer in the first set of layers. This layer uses a padding of 1 and a stride of 1, and 16 filters with kernel size of 3 by 3 to produce an output of 32 by 32 by 616. This is followed by 2n, or 6 convolutional layers. Each building block consists of 2 convolutional layers. The outputs of these layers are all 32 by 32 by 16 tensors. And this set of layers has 3 shortcut connections. Next, the second set of layers has another 2n, or 6 convolutional layers. The number of filters in each layer is 32. The first layer performs downsampling with a stride of 2. Then, the output of the first building block will be 16 by 16 by 32. Since the input and output dimensions are different, to configure a shortcut connection, the input dimension needs to be adjusted to match the output dimension. The input data is downsampled by a convolutional layer using a 1x1 kernel without padding. The outputs of these layers are all 16 by 16 by 32 tensors. In this way, we construct the third set of layers, and then we do global average pooling. Finally, the feed-forward network classifies the input image into 10 categories. Excluding the global average pooling layer, there are a total of 20 layers with trainable parameters represented by squares. This is the ResNet20 model for CFAR10 image classification. Now let's implement the ResNet20 model in code. Build and train a model for the case where n is 3, as shown in the figure on the previous page. Let's write a function that constructs a residual building block, and write a function that builds a ResNet20 layer. We'll take a closer look at these functions later, using the figure shown on the previous page. Read a CFAR10 dataset. The 10 categories are as follows. These are sample images. Each sample is a 32 by 32 by 3 RGB image. The first sample image is a horse, and the second sample is an automobile. Now we build a ResNet20 model for CFAR10 image classification. Create an input layer. The input layer receives 4-dimensional data like this. Next, we perform a simple data augmentation on the input image. Then we add a ResNet20 layer and a global average pooling layer. Finally, we add an output layer to classify the input image into 10 categories. Create and compile this model. Fit this model to the training data. The batch size is set to 256, and the number of iterations is set to 1,000. In the paper, it was repeated 64K times, but since it takes a long time, we will repeat it only 1K times. Next, let's check the loss history and measure the accuracy of the test data. Finally, let's check out some misclassified images. Before looking at the results of this code, let's take a closer look at the ResBlock and ResNet20 functions. First, we create the first convolutional layer using this code. The number of filters is 16, the kernel size is 3 by 3, and the stride value is 1 by 1. Apply 1 by 1 zero padding, batch normalization, and real U activation function. Then we add 3 residual blocks, each with 16 filters. This is a model where n is 3. Each residual block consists of 2 convolutional layers and 1 short connection. This code creates the first convolutional layer inside the residual block. Add a 1 by 1 padding to the input data and create a convolution layer with 3 by 3 kernels. And then we perform batch normalization and real U activation function. This code creates the second convolutional layer. Here we also add a 1 by 1 padding to the input data and add a convolution layer with 3 by 3 kernels. Batch normalization is performed, but rel U activation is not performed. This is the code that configures the shortcut connection. In this case, the input size and output size are the same, so we can just add them. Finally, we perform rel U activation and return the result. Add 3 residual blocks with 32 filters to the second set of layers. In this case, the input and output sizes of the first block are different. Therefore, to configure a shortcut connection, we need to adjust the input dimension to match the output dimension. Adjust the input dimension with a convolutional layer with a 1 by 1 kernel and stride values of 2. Finally, let's check the results of this code. During training, the training error and the test error are reduced like this. You can see that it learns normally without overfitting. The accuracy of the test data was 0.8324. The examples of misclassified images are as follows. The first image is actually a cat, but was misclassified as a deer. Let's run this code. It will take some time. We got the following results. This time, the accuracy of the test data is 0.8395. So far, we have looked at Residual Network and used it to classify CIFAR10 images. In the next video, we will look at 3D convolution.